Hello everyone, this video is about graphs and kinematics. So we have the first graph, AT graph, acceleration time graph. The area under the graph is the change in velocity. So the formula for acceleration is delta v over delta t, basically velocity divided by time. So velocity is acceleration times time, and when you have a multiplication, the relationship between the axes, this means the area under the graph is the product, or the v. So the v is the product, which is the area under the graph, and if the acceleration is horizontal like this, it's a constant acceleration. This is zero, constant velocity, and this is constant acceleration but negative, and the acceleration is linearly decreasing and acceleration linearly increasing here. In a VT graph, the area under the graph is the displacement or change in position, because v times t is displacement, v times t, the axis when you multiply. So multiplication means area under the graph. Gradient, the gradient is acceleration because it's v divided by t. Division means gradient. So when you have division relationships in the formula, then you're using the gradient. So here we have random acceleration because we have increasing, decreasing velocity. Here we have constant acceleration, the velocity is increasing linearly. Constant acceleration but negative, so we call this deceleration. And here we have zero acceleration because the velocity is constant. In an ST graph, we don't use the area under the graph, we only use the gradient. So the gradient is s divided by t, which is velocity. So division, because we use because of division, we use the gradient. The gradient is velocity, or s over t. So if the shape is a curve, if it's this kind of curve, which is part of like a smiley face, it's an acceleration. If it's part of a sad face, it's a deceleration. Well, actually the acceleration is positive, acceleration is negative. Okay, acceleration or deceleration, it depends on the velocity. So here we have part of a smiley face. This is positive acceleration because, although remember gradient means velocity, as you can see the velocity is bigger, the gradient is bigger in magnitude. So here the gradient is this big, so it's like -3 or -10, let's say, and the gradient gets smaller. This is like -5 and so on. So the gradient is getting smaller in magnitude, but it's negative. So this means the gradient is getting less negative, or we can say the gradient is actually increasing. Okay, so although the number is getting smaller, the gradient is getting smaller in number, but it's negative, so it's less negative. So we say that the velocity, the gradient is velocity, the gradient, which is the velocity, is getting less negative, or the velocity is increasing. So the acceleration is positive here, and this is also part of a smiley face. So here the velocity is smaller because the gradient is less steep, and then the gradient is steeper, so the velocity is increasing. And here it's part of a sad face, so this means we have negative acceleration because the velocity is steeper gradient, so bigger velocity, and the gradient is smaller, so we have a smaller velocity, so we have a negative acceleration. And here it's part of a sad face again, so the gradient is small in number but negative, and it's getting bigger in number but negative, so it's getting steeper. It's bigger in number because it is steeper, but it's negative, so it's getting more negative. so it's getting more negative, so that means it's getting or decreasing. So the we say we have a negative acceleration here. And for the velocity in this gradient, because increasing, decreasing, increasing, decreasing, we have like random velocity. If it's a straight line, we have a constant velocity, which is positive, and this is also constant velocity but negative. And here we have zero velocity because the displacement is not changing or the position is not changing, so the object is stationary here. And in summary, in an ST graph we only use the gradient. In a VT graph we use the gradient to find acceleration, and we use the area to find displacement or change in position. We don't use gradient in AT graph, we only use the area under the graph for the change in velocity. So for example, A was heading west from his home at constant acceleration from rest until reaching 10 meters per second. After 10 seconds, he left his wallet, so then he slowed down at constant acceleration to make a U-turn. So this is the slowing down part here, making a U-turn. 2 seconds later, he made the turn after accelerating at constant velocity. After accelerating at constant rate for 3 seconds, he reached 15 meters per second. He then slowed down and finally reached his home after a total of 20 seconds for his entire trip. So this is when the person is going, this is like the home, it's going, let's say, to the right, it's getting faster, the velocity is increasing to the 10 meters per second after 10 seconds, and then he realizes he left his wallet, so he's going back, so he's decelerating, still going to the right but slowing down, stops right here, and now he is going backwards, say to the left here. It's getting faster, the maximum speed is 15 here. After 3 seconds the speed is 15 meters per second to the left, and then it's decelerating, getting slower and slower and slower, and stops here. And the area under the graph is, if you just calculate the area of the triangle, we have 12 times 10 divided by 2, so we have 60 meters, and this is 8 times 15 divided by 2, so it's also 60. So the displacement is 0 because it's going back to where he started, but the total distance is 120. The acceleration, you can just use the gradient here. From 0 to 10, the acceleration is rise over run, so 10 divided by 10, which is 1. And from 10 to 12, it is 10 divided by 2, so 5. It's negative, so the velocity is positive but the acceleration is negative, so it's a deceleration. And here we have negative velocity and also negative acceleration, negative gradient. So actually we have an acceleration here, and here we have negative velocity, positive acceleration. So here it's going faster, slower, we have a deceleration again here. Alright, I'll see you again next time.